Happy Pi Day! This year, to find pi, the only calculation devices we're going to be using are human brains, and pens, and a lot of paper, and a room full of 30 people doing calculations for an entire weekend. And if the many, many tedious calculations here pay off, this will be the first time in over a century that people have calculated pi to this precision by hand. We are hoping for 100 digits. We'll see how we go. And we're doing it in the town of Houghtonleigh Spring? It's a town. And we're here for a very specific reason. Houghtonleigh Spring is a small town in the very north of England, between Durham and Newcastle, if you know those places. And the reason we're here in Houghton is because that building there is where the calculation by hand of pi to the most decimal places ever took place in the late 1800s. An individual named William Shanks was definitely living there in the 1861 census, right through until they died in 1882. They were running a private boarding school of 11 pupils, which meant William had some spare time. In the morning, they would get up, do some calculations by hand, then do boarding school things, and in the evening, double check their calculations. And it wasn't just pi, they did e, natural logarithms, the reciprocals of primes, all sorts of calculations, loads and loads and loads of tedious digits. And what did William Shanks do with them? Once they finished the calculation, they spammed the Royal Society. And so off I went to the Royal Society in London. I'm here with Keith, the head librarian at the Royal Society, and you've had a look through the archives.
I have indeed, yes.
And you've pulled out some of Shanks's original communications.
Exactly right, yeah. So these are the manuscripts that he sent into the Royal Society,
right,
hopefully for publication.
So people would send it in,
yep,
go, I've done a thing.
Done a thing, they'd send it to a fellow, that fellow would bring it to the Royal Society, read it to the fellows if they were lucky. If they weren't, they'd maybe publish it. If they were less lucky, they'd publish an abstract. Sometimes they just didn't publish it.
File it away.
Yeah.
And I've done previous videos on the Objectivity channel with Keith, looking at some of the things that never got published. Mm-hmm. And I didn't realise Shanks couldn't just send it straight into the Royal Society. He had to find someone he knew who was a member and get them to read it out to maybe get it published.
Yeah.
Okay, but these are the letters he sent in. What do we got?
Indeed. Well, let's start at the beginning over here. Right. So this one, we can see here on the extension of the values of the box, of the base of Napier's logarithms.
Oh, he's doing some logs.
Yeah, and it's William Shanks, Houghtonleigh Spring, Durham, communicated by George Biddle Airy, Astronomer Royal.
So you went straight to the Astronomer Royal?
Straight to the top.
And he's obviously worked out the values of some natural logarithms. Mm-hmm. He sent them to the Astronomer Royal, who's gone, good work, William.
Send it into the Royal Society.
We'll get it in there.
Yeah, absolutely right, yeah.
Well, we're not here for natural logs though, are we? What else have we got?
So here we have another manuscript. William Shanks again. There we go. So
extension of the value of E.
Yeah, numbers of digits.
Of pi.
So let's get to the paper itself. Here we go.
Here it is. Extension of the value of E to 735 places decimals. And of natural log of 2, natural log of 3, 5, all to 310 by W. Shanks. And then here it is. There's E.
Yep.
Square roots. In the value of pi and other constants containing an infinite number of decimal places, the number of times each digit occurs will tend to an equality, and in order to exhibit space. I go below tables. Oh, so he's gone through his value of pi and he's counted how often each digit appears, and then he's done a little distribution of the relative frequency, well, just the actual count of each value as you go through the hundreds all the way up to 707. Wow. So there's a whole thing about pi being a normal number, which means all the digits appear equally frequently. Shanks was like, this was cutting edge. No one else has seen this much pi before. And so he's gone through and he's just double checking if they occur with similar frequency. But that's not the actual value of pi he sent in. This is now.
No.
He's
so
just
this
doing
is a later paper. And we've got reciprocals of prime numbers here.
So we love doing reciprocals of primes.
Yep.
But there's
So
have you got the actual pi he sent in?
Isn't this good enough?
No, I'm a big fan of primes. Love primes, love logs, love E.
We kind of misplaced that
Misplaced that
manuscript. Yeah,
manuscript.
we don't have it any longer.
Oh
We don't
my
know if we sent
goodness.
it back to him or whether it was just disappeared from the archives, but it seems not to have been preserved. We just have the printed one.
Oh, I love the phrasing. It appears to have not been preserved. But they did publish it at the time.
They did.
So it was all printed.
Yep.
And so while you haven't got like the original handwritten one he sent in, you have got the published one.
That's right. And we have some letters relating
Well, you
to
know
it
what?
as well.
We're going to look through all the other papers that Shank sent in, do some reciprocals of primes. That will be on the Objectivity channel if you want to check that out. But right now, we're going to go up to the reading room. There's like
That's right, where we store the journals. So the proceedings will be up there, and we'll be able to see that original paper in all its glory.
Oh wow! So these are all the printed
output of the Royal Society. So we have the philosophical transactions there,
right?
Proceedings
of
of the Royal
those,
Society
and
here.
then these.
That's right.
And here it is.
This is the one.
This is the one. Proceedings of the Royal Society, 1872 to 1873. So all we got to do is have a quick look. Oh wow. Let's have a look here. Oh good, there's contents. And he was in 73. Look through, so June, I think it was earlier.
Page 318.
There it is, there it is.
Yeah.
On the extension of the numerical value of pi by William Shanks, nestled in between, on the heating of a disk by rapid rotation. Kind of want to read that one now, I'm being honest.
That's you'd want to do that at home, I think.
That's okay. And further observations on the temperature at which bacteria and their supposed germs, guess it was still controversial, germ theory.
Germ theory, yeah.
Supposed germs are killed when exposed to heat. Wow, look at that. And so you're right, so page 318, oh, they've done them a disservice, not.
Oh, you're going to make a number joke now.
It should have been 314.
Oh, of course you were.
Oh, I bet one of these earlier on here is like 4 pages long. And no one needs...
Who bagged
Here we go,
it?
this
Who
one.
bagged it?
If they'd taken out on the durability and preservation of iron ships and on riveted joints, which I think is in no way riveting, he would have been on page 314 anyway. Let's have a look here. Oh, there it is, 318. I went straight past it. There it is.
Yep.
On the extension of the numerical value of pi by William Shanks. Houghton Lee Spring, Durham. That's where I just was. Okay, this is a slight spoiler for later in the video, but he's worked out the inverse tan of a fifth and the inverse tan of 1/239, both to 709 digits, which means this is the value of pi to 707 digits. There it is, the then world record. Most pi worked out, done entirely by hand. Sadly,
It doesn't look like much on the page.
it does. No, you put it on the pen. No, yeah. And you could bring that up with like 3 keystrokes.
Yeah.
In like Wolfram Alpha or something. But at the time, that took him so long, days and days and days.
Kind of a third of a page, but how much of his
A
life?
third of a lifetime. However, he died thinking that was correct to 707 digits. And his mate G.G. Stokes thought it was correct. Obviously, everyone at the Proceedings of the Royal Society was happy with it. However, I mean, no one else double-checked it.
It was refereed. So,
No, that's true, exactly. It was wrong. So he thought it was right to 707 digits. The 528th digit is incorrect. And this wasn't spotted until the 1940s when someone got one of these newfangled desktop calculators, like a mechanical thing, crunched it through, found a mistake. Now,
we want to see that digit.
Exactly. I was just thinking. Thankfully, they're grouped in 5. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 rows. So that's 60 across. So to there is 480 digits. 490, 500, 510, 520. That 5 there is incorrect.
Right.
So I don't know what it should be, but if that's the 528th digit, I mean, he still had the world record.
Come on, he got a digit wrong.
I know.
That doesn't count, surely.
I know. Well, that's true. You should have to say it's correct to here, so you're not misleading anyone.
The shame of the Royal Society publishing it.
Well, I mean, no wonder they lost the original.
Yeah.
They were like, just hide the evidence, hide the evidence.
Enough.
So anyway, if you want to see a lot more of what William Shanks did, Keith and I we're going to go back down again.
We're going to see some more Shanks.
He sent in so much stuff. In this video, however, we need to get back to Houghton the Spring. Shanks's house is here. It is no longer a boarding school, so we couldn't set up there to do our calculation. However, just down the road and around the corner in Houghton is Keep Yes School, and they very kindly let us set up our calculation workshop in their school hall. We had the school hall for 2 days, and in addition to me, there were 28 volunteers who'd given up their weekend to help me calculate pi by hand. I had never organized anything on this scale with this many people doing calculations, but we started with what we thought was a pretty good plan. Human calculators are dotted around the room, different stations for doing different types and parts of the calculation. We've got all the blank paper over here. They're different colors corresponding to what part of the calculation is being done. Key is up on the wall there, and each sheet is just over 100 squares wide, so they can all be done to a precision of just over 100 digits each. And importantly, while they're being worked on, they have to stay in this half of the room, because over here we have a dividing line. This bit of warning tape is our calculation barrier. On this side of the line, you're allowed to get your phone out, you can check your laptop. Calculation devices are allowed on this side, which is why someone hilariously brought an abacus. There's also a slide rule here somewhere, but if you step onto this side of the line, there is nothing except for pure human thought. We are going to calculate pi using exactly the same formula that William Shanks was using so long ago. Here it is. It's called Machen's formula. It was developed in 1706 by John Machen, who was at Gresham College in London. And they actually used it at the time to calculate pi to 100 digits. Much like what we're doing, we could have done this in London. Could be a Machen thing. No, we're doing Shanks because they did more digits and we have aspirations. So Shanks got this formula, and much like us, first of all, we could do all of this and then get pi divided by 4. To make the grand conclusion a bit nicer, we're going to preemptively take this divide by 4 off, so it's just pi equals, and then that becomes a 16, and that becomes a 4 down there. So all we have to do is calculate the inverse tan, the arctan of 1/5, multiply that by 16, and then subtract 4 times the arctan of 1 divided by 239. Which leaves the question, how on earth do you calculate the arctan of a value by hand? However, we've pretty much reached the end of day 1 here. People are wrapping up their calculations. So much like us, you're going to have to wait until tomorrow morning. Day 2 in Houghton Lee Spring, and after everyone had obviously had a sensible evening and a good night's rest, we were ready to get back into the calculation. But how on earth are we going to do these arctans by hand? Here's how we're able to do arctans by hand, and we're using the fact that if you've got the inverse tan, the arctan of 1 over some number x, that equals an infinite series. It equals 1 over x, subtract 1 over 3x cubed plus 1 over 5x to the 5, and then that carries on. You then subtract, you add, you subtract, you add, and you go through all the odd powers, always with that power also as a coefficient out the front. So in our specific example, let's say we want to work out what 16 times the arctan of a 5th is. Well, we're going to kind of bake the 16 in. So what we need to work out, that equals, is going to be 16 over 5 minus 16 over 3 times 5 cubed plus 16 over 5 times 5 to the 5, a lot of 5s going on there, subtract 16 over 7 times 5 to the 7 plus so on. In terms of practically doing this, we actually have a separate calculation over here. So what we do is we start by working out what 16 over 5 is, and we know 5 squared is 25. And if you see here, if you were to, ignoring the coefficients, if you were to divide this by 25, you'd get the cubed. Divide that by 25, you'd get the power of 5. Keep dividing it by 5 squared. So actually here, if you divide that by 25, that would give you 16 over 5 cubed. If you divide that by 25, that would give you 16 over 5 to the 5. Divide that by 25, gives you 16 over 5 to the 7. We've been calling this the spine, because these are like the common terms, and each one gives you the next one just by dividing by 25, which is a reasonably straightforward computation. But then while that's happening, you can get each of these, and you can divide this one by 1, which happened very quickly, to be honest, to give you this one. You divide this one by 3 to get that term. That's a 3, by the way. You divide this one by 5, and you get this term. So one series of calculations is giving us the spine, and each one gives you the next one. But then you branch off each one to get the terms. And you've got to do that for 5, or 1 over 5. And then you've got to do that for 1 over 239. So we've been dividing each term in the spine by 239 squared to get the next one, and then getting the terms coming off the side, which is why, as you look around the room, you can see 4 different colored bits of paper, a different color for each spine for the 2 different arctans, and a different color for each series of terms for each of the arctans. The difficult part is in the doing. What we discovered pretty quickly, though, is if you're working your way down the spine, the problem is once you've done this calculation, there's only 2 more you can do. And this is a dead end because that's the finished term. Once you've done that one, there's only 2 more you can do. So this is kind of a bottleneck where we had more labor than we had calculations to do. People were sitting around with nothing to calculate. We tried to get a little bit clever. We realized as well as dividing by 25 to go 1 ahead, we could divide by 625 to jump 2 ahead, because that is 5 to the 4. So that's like doing 25 twice. And we also had an idea, what if we picked like a distant term and like started from scratch further down? So that's actually one of the calculations I was doing. I picked on the 239 spine, I decided, what if I jump way ahead in the 239 spine all the way out to 4 divided by 239 to the power of 9. So first of all, I worked out the 239 to the power of 9 times table. So this is 239 to the power of 9, and that's 2 times it, 3 times it, 4 times it, all the way down. And I have that, as you can see, it's been verified. It was checked by someone else who did the same table to make sure it was all correct. I fixed that mistake myself as I was going along. Once I had that times table, I could then divide 4 by this, and that looks a lot like this. So here's my calculation. I'll try and balance it on the board here. So this is 4 divided by 239 to the power of 9, and this is my long division, kind of just creeps down this way. And to save paper, because it's a big diagonal stripe at this point, I just wrapped it around. So I copied the bottom here to the top there, and then carried on down there. So I got the first 54 digits done. It's been verified to here. And then here, I think there was a mistake somewhere, but more than one other person had done this and verified it at the time. So I've abandoned my calculation because we're verified up to here, and then someone else has got the digits after that. That is the theory for how we're going to work this all out by hand, but I thought I'd go and ask some people what was actually happening in practice. Sophie, what are you doing?
So what we're doing at the moment is working on the 239 series, and we're doing it in parallel. So we have 3 teams. Currently, Thomas and Jeremy here are working on 4 divided by 239 to the power of 21.
Gotcha.
Now, when they have their answers, I'm writing it down 5 digits at a time, taking it over to Diana and Richard, who are on the next one.
Oh, right.
And then they can start calculating the next one before we've even finished this one.
So you're taking whatever's done here,
Yeah.
feeding it straight into the next calculation.
Yeah, so then they divide by 239 squared again. So that would be then 4 divided by 239 to the power of 23 in that case.
Gotcha, so we don't have to wait for them to finish.
Nope.
We're building the railroad in front of us as we go.
Yeah.
And then they're working on that. And in theory, we can then feed that into...
Well, that's the other thing. So here we have Lauren and Matt. So then not only am I giving Diana and Richard Jeremy and Thomas's answer, I'm also giving it to Lauren and Matt, who are then dividing it. So in this case, the 4 over 239 to the power of 21, they'll divide by 21 to get the term, stamp it, give it to Katie,
Amazing.
Done.
So it's all three are happening simultaneously.
Exactly, and because we've got 2 people on each, they're fact checking and checking it against each other. So we've got double verification. I'm here in case there is a dispute. There hasn't been yet. We're doing good, all right?
You're ready if there is. Gotcha.
Yeah.
All right, Katie, what are you doing?
I'm currently trying to work out where all of the different terms are.
And here you're marking down what's gone out, what's come in, what's been checked.
Yeah, in theory. There's a lot of bits of paper flying around here, but we're hopefully keeping track, and we've only got a few that are currently out being done, but we'll see what happens when they come back.
What's Adam doing? Adam's just comparing.
Adam is the keeper of all of the ones that we don't need anymore, basically.
Excellent.
But
That's good, that's important.
every so often we're like, oh, can we just check back against one
Right,
from
we-
like
well, an
5
old
terms
one,
ago,
got
and
it, got
Adam
it.
knows exactly where everything is.
William Shanks didn't just live in Houghtonleigh Spring, he died here as well. So during a break, I decided to see if I could go and find him.
This is Houghton Hillside Cemetery, where in 1882 William Shanks was buried. His wife didn't pass away until 1904, and then she was buried with him. However, much like how, after 527 digits, William lost his accuracy in his calculation of pi, and like the Royal Society lost his letters, in 1973, the town of Houghton lost William Shanks. They bulldozed a whole load of this, and they lost all the memorial markers. It wasn't until 2010 a local historian and some volunteers managed to unearth this, the original grave marker of Jane Shanks and William Shanks. It's now placed here in an arbitrary location in the cemetery, so if you want, you can come and visit it, and they're buried somewhere nearby. Classic Shanks.
Meanwhile, back in the Kepier School Hall, calculations were carrying along nicely. However, some people had gone rogue.
We have decided to start again.
Oh.
We're calculating the 1/239 terms, but
Yep.
just to 20 digits, because we want to check that the first 20 digits are definitely correct, so that we don't make an early mistake that leads everything else to be wrong.
Oh, nice. So you can then compare this against the longer calculations.
Yes. And we've realised it's a lot quicker to just do 20 digits and not do the rest of the 80. So we can do this very quickly, get 20 digits, and just confirm that at least some of it is going to be correct.
Oh, that's handy. And we're kind of testing out other methods we could have used.
Yeah, we've also worked out that it might be, it's almost certainly quicker to divide by 239 twice instead of dividing by 239 squared directly. Because you're dealing with 4-digit numbers, which are much quicker to subtract because we can do it in our heads without having to do lots of copying of the multiples and laborious subtraction.
Okay.
We've been referring to all of this as the calculating floor. Hazel, however, has taken that quite literally.
It's on the calculating floor. Hazel, what are you doing?
I have 2 calculations that are very, very different.
Oh.
So I am currently redoing it, and I have just spotted another mistake, actually. So it might need to be done for a 4th time, but we'll see when we get there.
So, roughly 80% of the way through our weekend adventure, Christian Lawson Perfect and Matthew Scroggs think they cracked. You think this is how Shanks actually did it?
Yeah.
Which is not how we're doing it.
No. We realised that dividing by smaller numbers is easier.
Correct.
And working in blocks of just a few digits is easier because it's easier to find a mistake and just repeat a small block.
Right.
So we've gone for working in blocks of 10 digits, and once that's done for one term, you can pass it on to the person computing the next term and then carry on computing more digits yourself.
So you used to do the first 10 digits,
Yeah.
and you work that down all the terms until it becomes all zeros,
Yeah.
and then you go back and do the next 10 digits all the way down.
Yeah, if there's one of you, if it's William Shanks, you do that. You work through all the terms until you get zeros and there's nothing left to do. And then you come back and add on 10 more digits to the first term, use that to get the second term, carry on and on and on. So what I've done with these people is they're each doing a different term. Someone at the end is doing 1/239.
Right.
The person to their left is doing 1/239 squared, and so on down to here. I'm doing 239 to the -6. So as each person on the right finishes a digit, the person to their left copies it, continues the long division, and it just comes down this line.
You're like a single William Shanks spread out over time.
Yeah, it's yeah. And then on the opposite side of the table, we've got people doing the division by an odd number to get the final.
To get the terms out. Gotcha. Nice. And does it feel faster, easier than what we were doing, or?
It feels easier, and I think it's faster because there's much less getting stuck and trying to work out where you are.
Yeah.
And also at any point in time, we could just stand up and know exactly how many digits of pi we've got.
The way we've been doing it is doing every term just to 100 digits before we get to the next one, which is good, but I think we've lost a lot of time trying to find and isolate and fix mistakes as they pop up, which this hasn't got that problem.
Yeah, we're not doing any error checking, but we could have a duplicate of us over there and just look over our shoulder and check every now and then.
Because over on the other side of the room, we're still doing it our way, but because we're nearing the end of the day and there's fewer tasks left, we decided to have this splinter group trying the Shanks method just to see what it's like, because a lot of the point of this is get some experience, see what works, see what doesn't work. This is working nicely.
Despite this breakthrough in calculating pi by hand, it was too late to change course. We had to see our plan through, and all of the terms were starting to come together.
So here we're adding all of the terms together. So we've got the 16 over 5 divided by 1, and then 5 to the 5 divided by 5, and then to the 9 divided by 9, 13 divided by 13, going up in 4s. And then we're doing the alternating terms, so 3, 7, 11, 15, going up by 4 each time. And we're going to add all these and subtract all of these, and hopefully we'll get the denominator of 5 term.
Time was now completely getting away from us. It was the end of day 2 and we had to clear out of the school hall. So frantically, we were adding all these last terms together, possibly a little too quickly. And then we just had to combine those two arctan values to get our final value of pi.
Right, so we have arctan. This is arctan a fifth, which we will verify later to see how well we did on that. Oh, sorry, you're right. We did 4 times arctan. 16 times that. This is the level of accuracy that I'm. Okay, here we go. So that's going to be a 1, 14 take 7 is 7. That's now a 5, 11 take 4 is 7. That's now a 0. That's now a 9. 15 take 8 is 7. 9 take away the 0 is still 9. 2 10 is a 7. 0, 6, 3, 5, 4, 1. Ooh, that's a 6. What was I doing? That's now a 13. That's a 5. Is that correct? Are people satisfied with that? 6, 8, 16 is 8, 8, 5, 3, 5, 6. 2. Oh, 2, that's a 12, that's a 9. That feels familiar. 7, 12 is a 5. 7, 6 is a 1. 5 and 1 is a 4. 1. Well, as far as I know... Uh-oh. For completeness, Jeremy, do you want to unveil the pi? Just say yes.
No.
3?
Yes.
Point?
Yes.
14159.
Yes.
2653.
Yes.
58.
Yes.
I think we're done here. 8?
No.
Ugh. What is it?
9.
6?
7.
8?
9.
2?
3.
9?
2.
8?
3.
I don't feel like they're getting closer together. Okay. I'm very tempted to count the 0th digit, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 correct digits. So just over a third of a digit each. Give yourself a medium round of applause. Oh. Get a panning shot of everyone's sad faces.
Look sad, please.
Now, for the record, we have actually got the correct values of 16 times arctan a fifth and 4 times arctan 1 over 239. So we will look at that afterwards, and future Matt will let us know where we went wrong. 3, 2, 8.
9, 5, 7.
Yep.
5, 9, 8.
That should be an 8. So that there, that's an 8 there. Wow. And then what happens?
0, 9, 2.
Nah, it's off, it's off. No, it's gone, it's gone.
The bottom one.
Yep.
Checking this well.
Yep. 31, 32, 33, 34, 35, 36, 37, 38, 39, 40 correct digits of arctan 1/239. Hi, it's future Matt. So we went wrong really early with arctan 1/5. I suspect it would be the final adding up because there were so many terms that had to be summed to give this. Whereas this one, each term was harder to do, but there were fewer of them. And so I think the final sum was easier to do. We got 40 correct, then one wrong, and then another 5, 10, 15 or so correct. There you are. So I think it's, once it goes permanently wrong, I feel like that's issues in the working out. But these little, like these bursts being wrong, might be the adding up, who knows? Yeah, or transcription error, could be anything. That's fine. So concludes the practice run.
There you have it. We got 11 digits of pi when we wanted 100. 11% success. And we knew towards the end we weren't going to do the full 100 digits. There were too many bottlenecks. It was taking too long. We actually had a lot of wasted capacity to do calculations, but there were none ready to be done. So we figured we were going to be around the 40, 50 digit range, and then I guarantee those final mistakes were because we had to add all those terms together at the end, and we didn't have enough time to verify them. So those final mistakes, I'm sure we got all the terms correct. A few mistakes managed to sneak in right at the end. But the important thing is, we tried, and we learned a lot. We gave it a go, and you better believe, one day, we will try again. But maybe not for a while.
Thank you so much for watching. We're all just packing up now. If you want to get involved in future years, details on that in a moment. However, first of all, I have to say this is the kind of high effort, niche viewership video which would only happen when it's funded by the viewers. So huge thanks to my Patreon supporters who have made all of this possible, the time, the effort, the expense, the work. So obviously loads of volunteers chipped in their time, which I'm hugely grateful to. All their names are below. Patreon supporters, I'm going to hack up the working that I actually did. I reckon I can cut this into squares with a minimum of 4 significant digits each. I'll sign the back. If you're in the statistically significant tier or higher at the end of March, I guarantee you can get one of these. There's a form below if you want one. If you're in a lower tier, if they're left, I will send out as many as I've got. So if you want one of these, whatever level you support me on Patreon, put your details below. I will do my best to get them to anyone, but I can only guarantee statistically significant or higher. Finally, we are absolutely going to try something like this again. And if you want to get involved, I've got another form below. You put your email address and your details in, and I will only contact you when I'm planning something along these lines in the future. So put your details in there if you want to be kept in the loop for this kind of tedious working out fun.